the particles are interacting, attracting, and repulsing. For this choice of alpha and beta, it tends to radially symmetric equilibrium distribution with sort of support on an annulus, so the 2D version of two intervals. Okay, and depending on the alpha and beta, you can have a single disk of support, or you can have annuli, or you can have much more exotic things. So I forget if that's the next slide. Oh no, that stopped working. Okay. Okay. Okay, and then in the random matrix series setting, this is familiar to people. You can also look at a stochastic version of these sort of interacting processes, but I won't say much about that. Okay, and then this is just saying that these are connected to eigenvalues of random matrices, so probably people in the audience are familiar with this. So there haven't actually been any talks on invariant ensembles, but that's so. So I guess it's worth mentioning that here there's a potential depending if the v is x squared, you get GUE, but you could look at other v's and you get other families of random matrices with other distributions. Okay. So how are we going to tackle this problem from a numerical standpoint? Well, we're going to use this formulation as an energy minimization problem. So we want to find the measure mu that minimizes this energy. And there's two great references. And I promise I've given this talk before. I didn't just put a picture of Percy's book just because he's in the audience. It was there before. That's actually where I sort of learned all this stuff, was trying to go through this book and understand it by doing numerics. But yeah. Okay. And again, the big question is, how do we compute this measure mu from this sort of energy minimization problem? All right. So now let's say we tackled it naively, which I guess actually Percy mentioned a genetic algorithm, which is something a bit more sophisticated than what I'm going to do, but that would be sort of, if you were going to tackle this problem, you want to find a measure that minimizes the energy. So let's put a bunch of point particles, find the point particle version that minimizes the energy. Why is this not maybe such a great idea? Well, if you have one charge, okay, obviously the minimum energy is going to be when it's at the bottom of these wells. When we have three charges, it gets a bit more complicated. So we have some energy coming from the potential, but also some energy coming from the interaction. So there's this question: is this the minimum? So these are all local minimums. So it's not a convex problem. There's many local minimums. This is one local minimum. If you plug it into an optimization package, it spits out this. Or if you start with a different initial guess and do conjugate gradient, you get another local minimum. So is this the local minimum, or is it this? And you can see roughly there's sort of, if there's n wells, if there's n particles and 3 wells, there's roughly n choose 3 possibilities. Okay, so when you get up to 20 charges, it becomes a lot of different possibilities. Of each of these is local minimum, and your optimization algorithm will get stuck at one of these. So of course, maybe with the genetic algorithm, it will do better, or a stochastic gradient descent, but you aren't necessarily going to converge to the global minimum because we want the global minimum. Okay. So here is another example of, so just to give you a flavor of what do these measures actually look like, here is that same 3-well example. And the other feature you have is, depending on alpha, you get different sort of supports to measure. So similar to here, depending on beta, you could have different supports. Here, with an external potential, it can sort of either be one interval of support, or say 2 or 3. Okay. But using the numerics I'll discuss, you can compute in these different settings, because obviously I made this picture. So, okay. The other feature is, for the log kernel case with external potential, we always have square root singularity. Well, almost always have square root singularities. I'll say something about that in a second. So this sort of gives us an idea. So even when we split into two, each interval of support has a square root singularity. So our measures are not, they're not very complicated measures. There's something smooth times square root singularities times the Chebyshev weight. Okay, so this gives us the idea is let's represent the measure as a smooth function times something with square root singularities. And then the question is sort of what's the support of the measure, and as well as how do we compute the measure. Okay. So that is sort of the setup. Let's see how we actually tackle this problem. So this is the outline of the rest of the talk. We're going to see how orthogonal polynomials can be used to get sparse discretizations of these operators, both in the first in the log kernel case and later in the power law case. That's really where the new stuff is. And then we'll see how having sparse discretizations of the operators leads naturally to a method for computing the equilibrium measures. Okay, first with the potential theory case, then later with the power law. Okay. So as I mentioned, we know the answer, well, based on the, well, both the analysis and the movie we just saw, that the measure will have square root singularity. So it's very natural to represent the measure. Let's say it has a single interval of support as a Chebyshev weight shifted to the interval AB times the polynomial. And if we have a Chebyshev weight, why not use the orthogonal polynomials with respect to that weight? Okay. We'll see later that the analog for power law kernels will be a Jacobi weight with Jacobi polynomials. Because we already saw in the movie that it looks like it has Jacobi singularity, so it's for power law, that's sort of the natural analog is use a Jacobi weight, and then you have this question of what the lambda is, but we'll get to that later. So now we've reduced the problem of finding a measure to something a little bit more tractable. We need to find A and B and the CNs. Okay, so it's become sort of a discrete problem. And we're going to do this as sort of a two-step thing. First, find the ABs, and then find the CNs, because finding the CNs will be linear. Okay. So this is sort of different ways we can formulate the same energy minimization problem. We can either start with this, or we can use Euler-Lagrange to look at this problem. And actually, I could have done the numerics directly on that, but it's a bit easier to think, to sort of differentiate and look at this problem. Okay. So here we want to find A, B, and those CNs so that this equation holds. And the key thing is if we know A, B, then this is actually linear in the CNs. So this is actually a linear problem if we know the support. So the only nonlinearity here is finding the support. Okay. All right. So now let's look at, for orthogonal polynomials, the log and Cauchy kernel. Okay. So we have these different operators. And so this was sort of motivated by some stuff I did in differential equations. And some of it is very well known in classical, but some of it was, this was just my own personal motivation rather than like a historical thing. But where we saw that by choosing the right sort of orthogonal polynomials, we could discretize differential equations with sparse discretizations. Now we want to do the same thing, but now instead of derivatives, we have the power law and the log kernel and also the Hilbert transform. Okay. So we have these two operators. I'm not going to say anything about the fractional Laplacian, but it sort of fits in this hierarchy that you have the log kernel, the Hilbert transform is the derivative, and then the fractional Laplacian is the derivative of the Hilbert transform. Okay. So how do we work out, and we're going to come back to this because really this is all very classical, but we want to adapt it to the non-classical case of power law kernels. So this is something many people will be familiar with, is how do we figure out the Hilbert transform of a weighted orthogonal polynomial? Orthogonal polynomials satisfy a three-term recurrence. And it turns out the Hilbert transform of weighted orthogonal polynomials, if we multiply by x, we just do x minus t plus t. And from this, we get, apart from the initial condition, from the n equals 0 case, that the Hilbert transform of weighted orthogonal polynomials satisfies the exact same three-term recurrence as orthogonal polynomials themselves. This, combined with the fact that the Hilbert transform of the Chebyshev weight is 0, tells us that we can do Hilbert transforms of weighted Chebyshev polynomials. So using these basic tools of recurrence relationships, you can show this fairly well-known formula. I mean, I think there's probably an extra minus sign that shouldn't be there, but whatever. Okay. And this is sort of telling us that if we use bases built out of Chebyshev polynomials, our Hilbert transform becomes essentially a diagonal matrix or a super subdiagonal matrix. So this tells us how to get a sparse discretization for operators involving Hilbert transforms. Okay. I'll also mention we can do the same thing if we just integrate this formula. We get a diagonal relationship for the log kernel of Chebyshev. Okay. All right. So that's gives us a way of discretizing essentially our problem. Our Hilbert transform of some measure is equal to some potential. If we know the support of the measure, that essentially is telling us that we have almost a diagonal matrix. What about if we have multiple intervals of support? Well, here the key idea is the effect of one interval on the other is a compact operator. So when we use polynomials to discretize these operators, it's going to be effectively a finite dimensional. The interaction between the two intervals will be essentially finite dimensional, provided these are separated sufficiently far. Okay, so here's actually, so I didn't do this plot because it would just be diagonal for one interval. When we have two intervals, or I guess three intervals, this is our discretization of the Hilbert transform using piecewise Chebyshev polynomials. We have the diagonal part from the interaction of the intervals on them with respect to themselves. Then there's the interaction between different intervals, but numerically they're compact, they exponentially decay, and so we get we can efficiently, if we know the support, we can compute the measure by essentially inverting this sparse matrix. Okay, so that's sort of the key idea. So that's how, if we know the support, if we know A and B, how do we find the CNs, including when there's multiple intervals? Well, that's a really interesting question. I mean, Jose would be the person to ask because there's a lot of open problems. So that's the interesting thing is like for the log kernel, there's not many open problems. For attractive repulsive, a lot of these questions are unknown. That's one of the roles that numerics plays, is that it gives you some understanding of what these measures should look like. Because we have these conditions, we still have these Euler-Lagrange conditions. If we compute the measure, we know we've done it correctly because we can test these conditions. So, he was asking, do we actually know a priori what the measures look like? So do we know that they are smooth times, are they sort of absolutely continuous? And the answer was, we don't, there's a lot of open. So in some settings, these are known. In other, for certain choices of alpha and beta, it's known. For other choices, it's not. And as well as there's sort of questions about dimensions. And you do get sort of collapse onto point measures. There's a lot of stuff that I don't actually know. Well, square root is only for the log kernel case, and then it's known. For alpha and beta, I think it's not actually known necessarily. I mean, maybe Timon knows more than I do. But. Yeah. Right. Right. We make a guess, we plug it in, the numeric spits something out. But once it's spitted out, we can check these conditions. Because in the power law kernel, it's just the exact same conditions, just instead of a log, it's that. So whether or not it was a good guess a priori, we know it was a good guess because it worked. And we know it worked because it matches these conditions. So, I mean, that's not necessarily a proof. You potentially could do sort of computer-based, like interval arithmetic, but yeah. Yeah, actually, I'll have some examples with different behavior. Okay. Okay, so this is sort of repeating what I already said. We use the Euler-Lagrange. We're actually going to just ignore this condition for the numerics. So that's sort of we solve this equation and check. Well, in theory, we check. I don't check, but I could have checked. And then we differentiate this. So we don't know this constant L. We could have solved it directly, but I didn't do that. So we differentiated, that unknown constant L disappears. We get this problem of essentially inverting the Hilbert transform. We saw that it was sparse. The only question is, how do we find the support so that the problem is linear? Okay. So let's start with the single interval case. So if I plug this into the single interval case, we have sort of, this is what our Hilbert transform looks like, that sort of diagonal thing. This is the expansion of the potential in Chebyshev T. We have these two unknowns, A and B. So A and B are sort of hidden in these Chebyshev coefficients depend on A and B. How do we choose A, B? Well, we have two unknowns, but we also have two conditions. One, that this is an invertible system, that 0 times that. So essentially, we need the zeroth Chebyshev T coefficient to be 0. So that's one condition. The other condition is that the solution must be a probability measure. Okay, so we have two conditions, two unknowns, whatever, do Newtonian iteration, and you can compute the Jacobians, because there's sort of a dependence on A and B, but automatic differentiation is so powerful these days, especially in Julia, that you almost don't need to think about it. Okay. And that's how we do the one interval example. So here's some plots, and I did include, so here's some potentials, and here's the corresponding measure. I did include one example, which shows that you don't always have square root singularities, but actually it's not, it's 3/2 or 5/2 or something like that. So it's still square root times something smooth. Okay, and I will mention that if you perturb slightly around this degenerate one, you get back square root singularities, and this is related to stuff by Tom Claeys, and Igor. Okay. So what about multiple intervals of support? Now we have two end conditions. So if we let's just assume we know how many intervals we need. Let's say n is 2. If n is 2, we have 4 unknowns. What are our conditions? We're going to get, so before we had one condition that the linear system was solvable. Here there's an analog, which gives us sort of, if n is 2, 2 conditions. Then we have that it's a probability measure, so that gives us 3 conditions. We need one more condition, which is that this constant L on each interval is the same. So that gives us 4 conditions. We have 4 conditions, 4 unknowns, use Newton iteration, and hope it converges. Okay. So here's sort of, again, that movie, but now as a plot, showing that depending on the alpha, we get different measures, but we different supports, but we can represent it as something smooth times square root singularity, plug it in, and use Newton iteration to get these supports. There's something subtle going on here, which is, I never said it's like a convex problem. And in fact, this equation I'm solving has multiple solutions. So this is thanks to John Papadopoulos. So and I forgot what alpha it is, but this is for some choice of alpha where the true equilibrium measure is on 3 intervals of support, but there are still local minimizers where, say, a local minimizer of that solves the equations that has 1 interval of support or 2 intervals of support, but we have those extra Euler-Lagrange conditions, so we can look at all these and figure out which one is the global minimizer. And it's much better than the discrete thing where you had sort of n choose 3 possible local minimizers. Here, there's very, very few. Okay. So you did this using sort of a deflation algorithm where you find one measure, then you sort of deflate around it and you can sort of pick up other ones. Okay. Okay, so that's the log kernel case. Now for the sort of new stuff, the power law, attractive repulsive. So the key idea here was we used Chebyshev basis, and then we found out the Hilbert transform had the same recurrence relationship as orthogonal polynomials. So our plan for attacking power law is to sort of essentially find a recurrence relationship that the power law kernel has when applied to orthogonal polynomials. Now, what do you do when you want to find a recurrence? Well, what do? I check the DLMF, and so I tried to find a DLM, something in the DLMF for this kernel applied to orthogonal polynomials. And it's sort of natural that we will want to use this basis for representing the measure. Unfortunately, I mean, these sort of look related, but they aren't really, and there was sort of nothing here of use. So if you squint your eyes, these kind of look like fractional integrals, but I don't think there's any relation. Okay, so we're sort of out of luck in terms of the DLMF. But there are known relationships for left-sided and right-sided fractional integrals. So let's replace the power law kernel by a sum of a left and a right fractional integral. Okay, and try to use, hopefully by decomposing in this way, we will simplify the problem. Okay, so now the question becomes, what do these do when we apply them to orthogonal polynomials? Okay, well, let's try that same trick that we did for the Hilbert transform. Let's multiply this left-sided fractional integral by x, do x minus t plus t. This term, we know the 3-term recurrence, so we get that. And we're left with this, but instead of alpha, it's alpha plus 1. Okay, so it didn't quite work out quite as nicely as the Hilbert transform. But these are fractional integrals, so integrating of alpha plus 1 is the same as integrating of alpha and integrating once. And if we use classical orthogonal polynomials, we know a sort of integral can be re-expanded in the same basis. So we can use the fact that integrating ultraspherical polynomials can be re-expanded back in ultraspherical polynomials. And putting everything together, this tells us that the left-sided fractional integral also satisfies a 3-term recurrence. Okay. Well, it's probably a 2-term recurrence where one of the terms is 0, but I also call it 3-term. Okay. So that tells us a left-sided recurrence relationship. We also have a right-sided integral recurrence relationship, and it turns out you can put these two together to get a recurrence relationship for these power law kernels applied to weighted ultraspherical polynomials with any parameter. So this is true for any alpha, any lambda, with some nice simple rational formulas. And this is, well, the first time I gave this talk, I put new in question marks, but then because it was the sort of thing that you feel must be somewhere hidden in some ancient Russian paper somewhere. And the referee also thought it was something that must be hidden in some ancient Russian paper. But unfortunately, the referee couldn't find the Russian paper where this is hidden. And after 5 rounds of revision, finally the paper was accepted. So, as far as I know, it's this is a new formula. Okay. All right. So now, yeah. Well, yeah. I say I didn't find, the referee didn't find. Yeah. Yeah. The thing, so this, lambda and alpha can be arbitrary. Yes. Okay. Yeah. So the referee mentioned this result is known when lambda and alpha are related, actually with the sort of relation we use for the here, but in the general case they weren't known, and we need the general case because we have an alpha and a beta that are different. Okay. Yeah. Okay. So now I didn't say what lambda we want to use. I didn't say what singularity we want to use. But if we only have one of these terms, then we sort of know based on, so in the log kernel case, we found the weight whose Hilbert transform was 0, or where the log kernel maps polynomials to polynomials. So we want to find the weight that has that property. And if we only have an alpha, it turns out we can choose the weight according to this rule so that these power log kernels map polynomials to polynomials. Okay. The way it's set up, it's not necessarily diagonal, but it is banded. So it's a map from polynomials to polynomials, and we get a banded system. All right. But now we actually have two different alpha and beta. And it turns, as far as we know, you can't simultaneously send both. So if we choose lambda based on alpha, beta will not map polynomials to polynomials, and vice versa. For reasons that I guess Timon knows, which I don't know. We choose one of them, I think, because it's the larger one or something. So we choose this alpha term. That is going to tell us our weight. But from the recurrence relationship, we know how to apply this operator for the other one. And it turns out the resulting matrix, well, it doesn't map polynomials to polynomials. It's not banded, but it is exponentially close to banded. So okay. All right. So, and then we can sort of plug that into the to the rest of the framework of choosing the support of the measure using iteration and so forth. Okay. And that's how we managed to produce this movie, which is the world's slowest movie. But this is showing how as beta increases from the first one to the second one, we get this sort of transition from one support to two supports. I might finish my talk and then start the movie over again because I'm almost out of time. Well, it goes really quick. It's slow and then quick. Well, this is perfect timing because now I can fix the microphone while Wow, the movie. Okay. I think it's going to do something soon. What? At 1.5. Okay. At 1.5. Okay, 1. Okay, here we go. And so you see and it has kind of this weird feature that it looked as if it didn't blow up. I don't know how much of that was a numerical effect versus sort of, and because there's a lot unknown about this and about the properties of the measures, we're not sure, but at least this gives us some sort of intuition about what might be going on. Okay. Yeah. So that's why it's very interesting, because it went 0 and then it blows up again. These are probably meant to be blow-ups. Yeah. That transition is also where the numerics breaks down, because you have you lose that one interval is a compact bother. Okay. Oh, that's the wrong computer. Okay. So finally, I won't go into any details, but a nice thing is that this all generalizes to higher dimensional problems, where instead of Jacobi polynomials or ultraspherical polynomials, we have generalized Zernecke polynomials. These are multivariate orthogonal polynomials on the disk. We don't know yet how to do annuli, but we're sort of working on it. And this uses Meyer G functions, which earlier in this week I said nobody likes Meyer G functions, and then a bunch of people said they like Meyer G functions. So apparently there are people who like Meyer G functions. All right. Okay. I sort of mentioned there's lots of open questions. Some things are known for some parameter regimes. There's a lot still to be done. I'll sort of finish there. There's a lot of open questions. One is, how do you do this in higher dimensions when it's not radially symmetric, as well as annuli? That's a really hard problem. This also is connected to equations involving fractional Laplacian. So if you see John's poster, it goes into some more detail. I'll leave this as a question mark, whether power log kernels come up anywhere in random matrix theory, which I'm not aware of. All right, I'll stop there.